Hello. In this video, I'm going to show you the very basics of how to use FPGAs. I first learned about FPGAs over a year ago, and in order to expand my knowledge base, I decided to make some small demo projects using one. I am by no means an expert in the field of digital circuit design. I've just found that the best way to see if you know something is to try to teach it to someone else. To that end, if you see a way that this video could be improved, either the video itself, the material, or both, please feel free to leave a comment. For this video, I'm going to assume that you know what an FPGA is and in what situations you would want to use one. I will be using the Lattice iStick, a development board from Lattice Semiconductor, which is available on DigiKey. The iStick uses the ICE40HX1K, one of Lattice's low-power FPGAs. The build software I am using is the Project IceStorm open source toolchain, and my computer is running Linux Mint 19. A link to Project IceStorm will be in the description. Here is a picture of what I'll be using. Please pardon the cable management or lack thereof. Along the top are 4 wires that are used as inputs. From left to right, they are A, B, C, and D. They are connected to the I/O pins in parallel with pull-down resistors. For output, I'll be using the 5 LEDs on the top side of the board. Relative to the camera, they are named top, right, bottom, left, and center. Not every one of these demonstrations uses all 5 LEDs, so the unused ones are left out of the programs. This poses an issue, however. For whatever reason, if an I/O pin is left unconstrained, it is left floating. For these 5 LEDs, that means they'll glow faintly if they're not in use. So when you see them glowing when they're not supposed to, it's not your computer and it's not my camera. It's just a minor annoyance that I haven't researched how to fix. This first demonstration won't do anything particularly remarkable. This will just show simple asynchronous and synchronous logic and how to use make, Icarus, and GTK-Wave. For this, we will need a Verilog source file, a pin constraints file, and a make file. First, we'll look at the Verilog source file, called basic.v. The first line is the module header, and defines the module's inputs and outputs. We can see that there is a clock input, 4 other inputs, and 4 outputs. Lines 3 and 4 define LED-T and LED-L, to both be wires and sets them to be assigned Boolean expressions. LED-T is assigned A and B, while LED-L is assigned A or B. This is an example of asynchronous logic. LED-T and LED-L will always be equal to their assigned expressions, even if the inputs change in between clock pulses. Line 8 begins an always block. After the keyword always is the block's sensitivity list. This is a list of what inputs will trigger the block to activate. Right now, the block is triggered only by the rising edge of the clock. Lines 10 and 11 assign values to LED-B and LED-R in much the same way that LED-T and LED-L were assigned. The key difference is the assignment operator. This is the synchronous assignment operator, which triggers when the always block does. The next file is the pin constraints file. This is a short file that defines how symbols are mapped to pins on the hardware. The values of these pins were found by comparing the datasheets for the iStick and the ICE40. The third file needed is the make file. This contains recipes for make to build the project and to build the Icarus simulation. The make file is shown here for reference, but I won't be explaining it because there are better makefile resources elsewhere on the internet. Simply put, running make by itself builds the Verilog source files into a bit stream that can be uploaded to the iStick, and running make test builds an executable that simulates the workings of the Verilog source. Here is a video of the code running on the hardware. I don't have any buttons on hand, so I'm just plugging the wires into the rails. As you can see, the left LED lights when either A or B are inserted into the positive rail. The top LED lights when both A and B are positive. The left and bottom LED have the same behavior. It is important to note that Icarus Verilog is an extension of System Verilog, the actual language that Verilog synthesizers use. Because of that, test bench code written for Icarus will not synthesize, meaning it won't actually run on the hardware. That is why the code being tested is written as a module that can be instantiated by the test bench. The first step to using Icarus is to write the simulation in Verilog as shown here. This file begins by declaring the module called test. It then declares and initializes 4 wires and 4 registers. Then, the first initial block sets the signal changes. The numbers after the hash marks indicate how many cycles the simulator waits before applying that signal change. The time step begins at 0. So, for instance, line 15 will occur at time step 3, and 3 steps later, line 16 will execute. For 2 events to occur simultaneously, the number of time steps is omitted, as on lines 17 and 22. For clarity, they are put on the same line, but they could be separated on different lines. On line 28, the finish command triggers at time step 51. On line 33, a single line always block inverts the clock every 5 time steps. This will create a clock with a 10 cycle period and a 50% duty cycle. Line 35 creates the device under test as a module. The type name of the module is basic because that is what the module was named. The name of this instance is DUT for device under test. This could be named anything, but DUT is as good as any. And finally, the clock, 4 test inputs and 4 outputs are fed into the parameter list. Line 36 starts an initial block that creates an output file and writes data to it. These lines could have been in the earlier initial block, but when I wrote this, the data file was an afterthought. Building this with make test and running the executable with VVP test results in an output file called test.vcd. Shown here is the resulting VCD file plotted in GTK wave. It shows the clock wave, the 4 test inputs, the 4 LED outputs, and 2 comment lines to break up the clutter. The green lines indicate the value of a signal, and the red blocks indicate that a value is unknown. Several markers have been placed that indicate where events have occurred, which we will go through. The first marker is marker A at timestamp 3. At this point, test A goes high, which causes LED 1 to also go high. At timestamp 6, test A goes low and LED 1 with it. Recall that LED 0 was assigned the value test A and test B, while LED 1 was assigned the value test A or test B. At marker B, both test A and test B go high, and LED 0 and 1 with them. It is important to note that in the basic module, LED 0 and 1 are wires and changes in their values are not synchronized to the clock. This is contrasted by marker C, where test C goes high. The change is not applied to LED 3 until marker D, where the rising edge of the clock pulse occurs. This is because LED 2 and 3 are driven by registers, which only change on the rising edge of the clock. Likewise, test D goes high at marker E, but the changes are not applied until marker F. If input values are changed before a clock pulse can occur, they will be ignored. This can be seen in markers G and H, where test C and test D go low and then test C goes high again. This results in LED 2 going low on the next clock cycle, while LED 3 stays high. As a final note on Icarus, it has many other features not used here. You can, for instance, create multiple devices under test, pass command line arguments, or load test data from a file. A link to the Icarus documentation will be in the description. The next example I'm going to show is an extremely basic example of a blinking LED. Every programming language has its own version of Hello World, and this blink module is one example. It uses the same makefile and pin definitions as the previous example, so I won't show them here. There are two features here to note that this example has that were not explored in the previous examples. The first is on line 3, where the counter register is declared. In the previous example, all registers and wires were a single bit wide, while this counter register is 25 bits wide. The first number in the brackets is 24 because bit 24 is the most significant bit, while bit 0 is the least significant bit. The second new feature is on lines 7 and 8. Line 7 increments the counter in much the same way as other languages do, but line 8 assigns bit 24 of the counter to the LED. It is important to note that because these lines are contained within an always block that triggers on the rising edge of the clock, these lines will execute simultaneously, but not sequentially. If bit 24 of the counter is set during one clock cycle, the LED will not be set until the following cycle. This can be verified experimentally using a simulation, but that is left as an exercise to the viewer. Here is a video of the example working. The LED has a period of about 2.8 seconds. The size of the counter was chosen because each bit of this kind of counter cycles at half the frequency of the next least significant bit. The datasheet for the iStick says it has a 12 MHz clock, so bit 0 of the counter has a frequency of 6 MHz. Bit 1 is 3 MHz, and so on. Following this pattern, bit 24 has a frequency of 0.36 Hz, which is a period of about 2.8 seconds. The next example is button debouncing. Button debouncing is a common task in hardware design. Buttons are held in place by springs, and sometimes when buttons are knocked or vibrated, the contacts can momentarily close or open or bounce. Debouncing requires the button to be held in place for a certain amount of time before the internal state changes. This example has two modules, the debounce module and the top module. This module is a little involved and takes some explanation. The always block on lines 6 through 10 make a 2-bit first-in, first-out buffer. This ensures that the input from the switch is delayed at least 2 clock cycles. The second always block contains the first instance of branching logic in this video. The first branch simply resets the counter to 0 if the state hasn't changed. The second branch increments the clock and enters another branch. The syntax of the finished wire on line 13 says that finished will be high if all bits in the counter are high. Basically, all the bits of the counter are ANDed together. If that condition is true, then the state is toggled. Lines 31 and 32 create signals that only trigger for a single cycle. The only time where idle is false and finished is true is the clock cycle where count is all ones. In the declaration of this module, the output register is initialized to 0. This is for the sake of the simulator. If it wasn't given an initial state, the simulator would give it the value uninitialized, and the simulation wouldn't run correctly. In real hardware, this wouldn't be needed because all logic gates would have a binary value at startup. In this simulation, the input is pulsed momentarily at the beginning for 2 time steps or 1 clock pulse. As you can see, the pulse move through the buffer and trigger the counter for 1 clock cycle before the system resets. At marker A, the input is triggered and maintained, and at marker B, the counter is finished and trans up goes high for a single clock cycle. At marker C, the input is released and eventually trans down goes high for a single cycle. The features of this module have already been discussed earlier in the video. All it does is tie the relevant wires to the debounce module and toggles LED T and LED B in time with the clock. Here is a video of the final result running. You can see that the center LED matches the state of the button, while the top and bottom only toggle when the button is pushed or released. The final demonstration is of pulse width modulation, or PWM. PWM is used to control a variety of voltage-controlled devices, such as lights and motors. The principle of operation of PWM is to turn a circuit on and off rapidly, thereby delivering only a portion of the power that a DC signal would. This is achieved using a counter and a threshold. The counter starts at 0 and counts up, and if the counter is less than the threshold, the output is high, otherwise the output is low. A PWM signal can be described by two properties: the signal period and duty cycle. The period is the length of time that the counter runs. For instance, if the counter resets every millisecond, then that is the signal's period. The duty cycle is the length of time that the counter is less than the threshold and is usually measured as a percentage of the period. For instance, if the period of a signal is 1000 microseconds and the signal is high for 200 microseconds, then that is a 20% duty cycle. The threshold and counter are implemented as 8-bit registers in this module. The counter increments every clock cycle, and if the counter is less than the threshold, the output is high, otherwise it is low. The counter counts from 0 to 255, and with a 12 MHz clock, it rolls over about every 21.3 microseconds. That gives a PWM frequency of just over 46.8 kHz. This is the output wave from the test bench. At marker A, the threshold is set, and the output is high from marker B until marker C. It is worth pointing out that because the threshold is set in the middle of the counter's cycle, the output is not high for the full 7 clock cycles. This isn't that important, however, because the PWM signal cycles too quickly to be noticed. PWM is also typically used for devices that don't care about precise timing, and they won't notice a missing microsecond. This is the top module, which provides an interface between the buttons and the PWM module. What's new and interesting about this is how the threshold register is changed. On line 17, if go up is high, then the threshold is shifted left by 1 and then incremented. And on line 22, if go down is high, then threshold is shifted right by 1. I did this to account for underflow and overflow conditions. If a variable is an unsigned integer and has a value of 0, then subtracting from it will cause it to underflow and become its maximum value. If it is at its maximum value and is added to, the opposite will occur. The value will overflow to 0. Shifting left and right are equivalent to multiplying and dividing by 2, but an interesting effect happens at extreme values. If a variable is at its maximum value, that is all ones, then shifting left will push the most significant bits off and the least significant bits will be filled with zeros. Doing this repeatedly will cause the value to decrease, if the most significant bit is a 1. This can be mitigated by incrementing the value. If a value is all ones, then shifting left and incrementing leaves the value unchanged. At the other extreme, right shifting a value of 0 leaves the value unchanged. 0 divided by 2 is still 0. This has the effect of preventing over and underflows without needing to check a carry bit. It also has the effect of reducing the number of light levels the system can produce, which might be useful depending on the intended application. Finally, here is a video of the project working. As you can see, after hitting the maximum brightness, the up button does nothing. This is likewise for when the LED is off and continuing to trigger the down button. This concludes my demonstration of these beginning projects. If you would like to add information or make suggestions on how the video can be improved, please leave a comment down below.